I can get started. Okay, so the first speaker today is Michael Wheeler from University of Melbourne, and he's going to talk about colored vertex models, orthogonal functions, and probability. Oh, and just one note, yesterday it was slightly unclear. The speaker has 1 hour, and the 15 invisible minutes in the schedule are actually questions. Not that you can't interrupt during the talk, but you have 15 minutes for questions after 1 hour. Okay, thank you, Michael. Go ahead.
Okay, thank you very much, Rinat. Also, thanks very much to the organizers for...
Wait, we can't hear you. Oh, okay.
Oh, you can't hear me?
Okay, good.
Okay, I'll start again. So yeah, thanks, Rinat. Thanks very much to the organizers for the invitation to speak here. So yeah, I'm going to try to give sort of a whirlwind tour of the world of what are called colored vertex models. And it's actually a subject that is quite old. Certainly the models that I'm going to talk about have been known for a very long time, going back all the way to the 1980s. So from that point of view, nothing that I'll say here is terribly new. But I suppose the connections with multivariable orthogonal functions and various nice combinatorial features, that's really I guess the new aspect of the work. And if anyone is looking for a sort of reference outside of anything that I might say here, so this is I don't know if people can see, this is the text that I wrote a few years ago with Alexei Borodin, and it's called Colored Stochastic Vertex Models and Their Spectral Theory. And I'll try to follow the exposition in there fairly closely, but hopefully at a less technical level. And I've tried, at least for the first lecture, to make it generally accessible to people who may not have any expertise in vertex models whatsoever. So I'll try to be very self-contained and thorough at least in the first lecture. So yeah, please feel free to interrupt with any questions you may have. So yeah, I'll start with just something very basic, which is actually what is the definition of a vertex. So when people talk about vertex models, a vertex has a very specific meaning, and so I'll try to give that now. So this will be definition number 1. So a vertex is the intersection of two oriented lines. So we'll see in a second why the orientation of the lines is important. But it has some extra data associated to it. So the first thing, together with two variables, which I'll usually denote x and y, you could think of these as complex variables or indeterminates, depending on how you want to interpret things. It really doesn't matter too much. So two variables, which will be continuous, and 4 discrete variables. Which I'll usually write as I, J, K, and L. And these will take values in some discrete set, which I'll say more about as we get going. Okay, so that's basically what a vertex is. And usually people draw a picture behind these things. So this is going to be our vertex. And so the I, J, K, and L, these are going to be states that you associate to the 4 edges that are connected to the point of intersection. And also the x and y, these will be associated to the 2 lines. So x, you can think of it as sort of flowing along this line here, and y is flowing along the other line. Okay, so this is basically what a vertex is going to be. And usually the interest behind these type of pictures is I actually want to associate to that thing a weight function, which I'll denote as little w. And the weight function depends on the ratio of those 2 continuous parameters, y and x. And it also depends on the 4 discrete variables that put around the edges of the vertex. So I write as W y over x, ijkl. Okay, so just some terminology for people who may not be familiar with this kind of thing. So x and y, these are usually what are called spectral parameters. I may just refer to those as spectral parameters as we go. And the four variables around the edges, these are going to be what are called state variables. And in particular, I will refer to I and j as being incoming states. Okay, so there's a kind of time flow which is built into these models, which is indicated by the arrows. So basically, I and j is what comes into the vertex, and k and l will be what comes out. So yeah, k and l will be the outgoing states. Okay, and you should think of this this weight function as basically being a map from such a picture to an element of the complex plane. So this is typically going to be some complex valued function. But because we want to make some connections with probability theory, it turns out to be convenient in many instances to assume the following. So we will often assume that this W actually lives in the reals, and more specifically in the interval 0, 1. Okay, so you can sort of take that as a working assumption from the very beginning. And that's going to ultimately allow us to interpret these vertices as probabilities. Okay, so at this stage, I didn't say very much at all. This is a very sort of general discussion. And in order to say more precisely what we're dealing with, you need to say something about the set that the state variables actually live in. So in particular, this S here. So in these lectures, S is going to be something very simple.
Can I ask a question?
Yes.
Is W symmetric upon exchanging the two lines, X and Y, I and J, and K and L?
So W does have some inbuilt symmetries. At this stage, that symmetry is not yet apparent. So at this stage, it could be anything. But once we actually start to talk about specific values for W, I think you will see that a symmetry like that holds, or something very close to it. Yes.
Okay, thanks.
Okay. So in these lectures, we're going to assume that S is the following set. So basically the set of integers from 0 up to n. And I'm going to refer to the elements of this set as being colors. Okay, so actually all of them, including 0, I'm just going to give them the name colors. And here n, I haven't said what this is. So n, this is actually related to the rank of a Lie algebra. So behind all of these models that I will talk about, there is a rich algebraic structure, and we're kind of leveraging that at all stages in the work. So more specifically, so our models will basically come from sort of a universal structure, which is usually called a quantum group. So it'll be UQ of SLN plus 1, so affine SLN plus 1. Okay. And so more precisely, the type of model that we'll deal with was considered in paper by Jimbo in, I think, 1985 or 1986. So certainly, as I said, the models are by no means new. It's not like we're reinventing the wheel, but this is what we're going to use. All right. So I think also it'll be a little bit awkward to always write this from 0 up to n. So I will just use the standard 0 bracket n to denote this set in what follows. All right, so let's move on. I probably will need to say a little bit more about the specifics of the model because at this stage it's very general. Okay, so definition number 2, and this is something that we refer to as conservation. So we will assume in what follows that the weight, which we defined previously, so W of y over x, ij k l, we will assume that this thing is identically equal to 0 unless the following condition holds. And so the condition is that if I take basically the set consisting of the element I, and I take its union with the set consisting of the element j, this needs to be equal to the union of k and l. Okay, and you should think of these unions as being in the sense of multi-sets. So, in particular, if I and j are equal, then when I take their union, it's like I have 2 copies of the same element. Okay, so this property here, this is called conservation, or I can say conservation through a vertex. And so in words, what it means is whatever states come into the vertex have to exit it. Okay. So maybe I'll do just a little example, and then that will make clear what the definition is. So example number 1. So suppose I have the following vertex. Yeah, I may change slightly the way I draw the vertices depending on the situation. So let's suppose I have maybe these 2 edges being both equal to 0 and these ones both being equal to 1. Okay, so this obeys conservation. Okay, why is that? Well, if I take the union of these 2 things, clearly that will be equal to the union of these 2. Okay, but it's not too difficult to come up with an example where this is violated. So, for example, if I have 2 1s entering and maybe I have a 0 here and a 2, this violates conservation. And I chose that example because it sort of illustrates a kind of pitfall that you can fall into. So the conservation property is not saying that I plus j should be equal to k plus l. And note that the vertex that I just drew, that would actually be true. It is precisely not this. It's rather saying that the addition of those 2 things as sets should be preserved when you travel through the vertex. Okay. So the reason why we sort of want conservation to hold is it leads to a nice interpretation of these models in terms of lattice paths. So if you think about it, if what comes into the vertex has to leave the vertex, there's a sort of natural way to identify this thing with lattice paths, which is completely standard. And that's simply to draw some colored edges on the vertex. And so these green edges that I'm drawing here, this would represent the motion of a path of color 1. And likewise, you could do the same thing for this path of color 0. Although in many applications, usually 0, we kind of just don't draw it. We only draw, say, all of the paths with positive index. Okay. All right. So hopefully this is all pretty clear at this stage. So now let's move on to something a little more technical. So this will be the third definition. Okay, so for vertices, actually before I do that, I want to define something else. So let's set up some notation. So define. I'm just going to define a function that's going to show up in all of the vertex weights that we're about to write down. So it's going to be a function b of z And it's just going to be the rational function 1 minus z divided by 1 minus qz. Okay, so this z here is going to be related to the spectral parameters of the model. And the q, this is a new parameter. But as I said before, there is really an underlying quantum group in all of this. And so the q that I'm writing down here is precisely coming from the quantum group. Okay, so all of our weights are going to depend on the spectral parameters and also on this variable q. Okay, so we define this function b of z. Okay, then all vertices that obey conservation. Okay, so I'm automatically filtering out all of the ones that are equal to 0. Have the following explicit weights. Okay, so there's actually not so many cases to consider because this conservation is a very stringent requirement on the vertices. So actually, there are really only three possibilities that can occur. So I'll draw these here. So here's the first one. So the first one is when I have basically both of the incoming states are going to be the same color, K. And in that case, by conservation, each of the outgoing ones has to be equal to K as well. So in this case, the weight W y over X. Actually, I will delete the y over X and just write Z in what follows. So W of Z with 4 Ks is going to be equal to 1 in this case. All right, so this is a kind of very simple case. All of the colors are the same. In that case, we will set the vertex weight equal to 1. And then there are two sort of more interesting cases, which are these. So let's suppose I have a color I coming in here and a color J there. And likewise, color I going out here and color J going out there. So in this case, I'll write W of Z, I, J, and that's going to be equal to the following function. So it's going to be U to indicate a function that I is greater than J times B of Z. So that's this B of Z that I introduced just above. Okay. And the final case is where I have, let's say, I and J entering in the same positions, but now they get exchanged at the top. So here I have J and here I have I. And so in that situation, I have W of Z, I, J, J, I. And we'll define this thing to be 1 minus Q to the indicator that I is greater than J, B of Z. Okay, and I haven't actually told you what is the Z here. I kind of hinted at it before. So I'm identifying Z here with Y over X. So all of these weights just depend on the ratio of those two spectral parameters, X and Y. Okay, so this is going to be the model that we work with basically throughout all of the lectures. Okay, are there any questions at this stage? Okay.
Can you hear me?
Yes.
Question, what means the notation y bigger than j?
Oh, sorry, I can't explain that. Yes, so this is the indicator function. So one of x, it's a logical function basically. So this thing is equal to 1 if the statement x is true, and 0 if x is false. Okay, basically a Boolean type function. All right, so whenever the condition I greater than j is satisfied, you will get a power of q. And if it's not satisfied, you just get 1. It's possible to write the weights in a slightly more explicit form without the indicator function, but I went for this because it's a little more compact. All right. So maybe let's do a second example, which will make things maybe a little more explicit than they are here. So example number 2 is to look at these weights explicitly in the case n is equal to 1. All right, so recall that we have our set S, which consists of the elements 0 up to n. So in the case n is equal to 1, this model is something very famous, and this is the 6 vertex model. So I'll try to reproduce the vertices that one gets for that. Maybe actually, I think I have a. Yeah, I might cheat and just copy and paste this this thing. Yeah, I might run out of room. Basically, there will be 2 which can kind of go in one column, so this should be fine. All right, so let's write these things out explicitly. So we're looking at the case n equals 1. So we only have 2 possible colors, 0 and 1. And if you think about it, there are precisely six possibilities that respect conservation around the vertex. And these are the following. So all zeros or all ones. And according to the weights that we gave above, in this situation, the weight is just 1. Okay, but then there are these cases here. So let's suppose I have 0, 0, 1, 1, or I could have 0, 1, 0, 1. I can have 1, 0. Yes, and I can also have this. Okay, so that's all 6 possibilities. And I'll just record very quickly what these weights end up being. Okay, so I'm writing them out in the fully most explicit form. Okay, that's what we have. And so indeed, you see that these are just some rational functions in the 3 parameters in the game, x, y, and q. And this is the 6 vertex model. All right, so I think there's going to be some problem session tomorrow. So basically, I'm going to intersperse throughout this first lecture a number of problems. Most of them are fairly easy. So I'll give the first one now. So problem number 1. So it's in 2 parts. So the first part of the problem is to determine the number, I'll call it A sub n, of vertices that respect conservation. In the general n model. Okay, so the n equals 1 example is above. Try to get a closed form for these numbers for generic n. That's just a simple enumeration problem. And then for n equals 2, draw all vertices explicitly and record their weights. Okay, so that's kind of just a little warm-up exercise for getting familiar with the model that we're dealing with. All right. Good. I will carry on. So let's come to the first, I guess, kind of result, even though it's not very deep. The proposition number one, which is going to be. Sorry, is there a question? Sorry, I can't actually hear the question.
Is this from online? Is there somebody online have a question? Can you put it in the chat if you do? I don't think it's a question.
Okay. Right, so proposition number one, stochasticity. So this is really the first fact behind the model. And that's the reason why we end up getting the links with probability. And so there's two parts to this statement. All right. So for any fixed vector ij that lives in this 0n squared in this case. So I take a vector of two colors. We have the following property. So basically, if I take a sum over k and l that live in our state space with the following vertex, maybe I'll draw it in the more canonical form that we did at the start, like this. So I'm fixing I and j that live along the bottom, and I'm now summing over k and l that live along the top of the vertex. Okay. And as before, I have x and y here. So whenever I draw this kind of thing here, or write, a sum over such vertices, it literally means compute the weight of each of the vertices and add them up. And so the claim is that for any I and j that you have as incoming states, this thing adds up to 1. All right. And that's actually very easy to see from the definition of the weights. So up here, it's just manifest. All right. So basically, this first vertex here, here you're fixing your incoming states to be both equal to k. In that case, there is only one possibility for what happens along here. It's completely deterministic. And so indeed, that weight is equal to 1. And then these remaining two vertices are sort of the non-trivial case where you fix what happens along the bottom. So it's the same along the bottom for both of these two. But then when you sum over the possibilities at the top, you do indeed find that sum of these two things is equal to 1. So this is the stochastic property of the model. And so in terms of probabilistic applications, what this is going to mean, it's going to allow us to put a probability distribution on this outgoing vector here. So k and l, I can think of this as some outgoing vector of colors. And basically, there is a distribution induced on these now, which is basically coming from this property here.
Can I ask a question?
Yes.
When you gave the example of the 6-vertex model, so this is apparently the stochastic 6-vertex model. Is it the most general one or the special case of the 6-vertex model?
Yeah, this should be the most general version of stochastic 6-vertex model. So yeah, I should say that so not really touching in this lecture upon what are called higher spin vertex models. So there are more general types of vertex model that you can define. Basically, where the states that live around the edges, instead of just being single integers, they can actually be multi-sets now. So I can, instead of having like a single color that goes through this edge, I can actually have multiple colors, right? So it's possible to define stochastic weights for these models as well, but I'm not going to talk about that at all. So if you're really talking about the honest 6-vertex model, this is the most general version.
So most stochastic is not the only version of 6-vertex, right?
Yeah, that's correct. So
is that your question? There is a non-stochastic version.
There is absolutely a non-stochastic version. So, for example, if one looks in Baxter's book, you will see a version that looks a lot more symmetric than this. And there, the stochastic property does not hold. Basically, what has happened here is you take those known solutions of quantum Yang-Baxter equation, and you perform some combination of gauge transformations and Drinfeld twists, and you can then massage them into this stochastic form. The downside of it is that the model ends up looking quite asymmetric, but it does satisfy a stochastic property.
Sorry, I have another question about this.
Yes.
But is there any, do you have any idea when you can make a solution to the Yang-Baxter equation stochastic, or there's no general?
Yeah, my basic understanding is you can do it for almost every solution of the Yang-Baxter equation. So I think this fact is not really written anywhere in the literature, but I would almost put as a kind of conjecture that if you take all of the R matrices in Jimbo's 1986 paper, all of these can be made stochastic via some simple gauge transformations and twists.
Okay, which is a guess. So yeah.
Well, it's a guess in the sense that it's not written, but yeah, I believe this is true.
I believe Borodin wrote something about this.
So there is something called a stochasticization procedure, which allows you to start from a non-stochastic vertex model and map it to a stochastic one. There is a catch, however. When you apply this procedure, in the process, the model you get out of this is a dynamical model. So it will have a height parameter in it. So it's no longer truly a vertex model. So there is such a procedure, but I don't think it's quite related to the question that was asked before. Okay. All right. Yeah, so this is the stochasticity. And there's actually a kind of reverse stochasticity as well, which is quite interesting. So I'll record that here as well. So now instead of fixing the incoming states, I'll fix the outgoing states. So for any fixed K and L, again, living in Cartesian product of the state space, we have the following. So now I'm going to sum over I and j, and I need to put a Q factor in here. So it's going to be, again, Q to the indicator that j is greater than I. And basically the same picture as here. Just copy it. Okay, except now that I'm fixing the top instead of the bottom. And this is equal to Q to the indicator that K is greater than L. Okay, so it's very similar to the stochastic property. And indeed, if you take this Q factor that lives on this side and normalize the whole equation, you can again convert it into a kind of reverse stochastic property. So for this particular example, it's as I said, you're fixing the states that live here, and it's then inducing a probability distribution on the bottom two edges. So one could think of this as being like kind of time reversal of the original Markov process. All right. All right, so that's probably everything I want to say about that. So next, I'm going to talk about some of the other properties of the model, which are very well known and certainly will be familiar to many members of the audience. So proposition number 2, this is going to be what's called the unitarity condition of the model. Okay, so to state this one, I'm going to fix basically 4 indices. So for any fixed, let's call them I1, I2, J1, and J2 that live in 0 to n to 4, we're going to define the following quantity. So I'll write it as U of I1, I2, J1, J2. And it's going to be the following object. So I'll have one line that sort of goes straight. And then the other line is going to cross the first in 2 places, like this. Okay, so what's happening now is we're actually concatenating 2 vertices, right? So the vertices we have, there's one living here and there's another one living here. And the convention for concatenation is that every time you have an edge, such as this edge here, which is internal, so it's joining this 2 vertices inside of your lattice. So if I have an internal edge, and here is another one, then I should sum over the states that are assigned to those edges. So basically, when I draw such a picture, there's actually 2 sums going on here. One sum is for basically this edge here, and the second sum is happening for this edge here. Okay, so let's complete the picture. So I'll put I1, I2, and J1, J2. And I'll also need 2 parameters, x and y, which are going to be my usual spectral parameters. Okay, so this is our quantity. Hopefully the definition is clear. So then there holds the following, that U of I1, I2, J1, J2 is equal to product of indicator functions. So basically, it imposes that I1 needs to be equal to J1 and I2 needs to be equal to J2. Okay, so if both of those properties are satisfied, this object is equal to 1, and if one of them fails, then object is equal to 0. And in terms of the kind of pictures, you might think of this as basically being the freedom to take I have these 2 lines that cross each other, and this is sort of the freedom to take this kind of loop and drag it across like this, so that the lines no longer intersect. So I can just represent it as 2 lines that actually never see each other. And in terms of knot theory, this is precisely one of the so-called Reidemeister moves. And we're about to see another one as well. Okay, so in terms of the problem set, so problem number 2 is to prove this. Using the explicit form of the weights that has been given.
Question on the weight. You define the weight of a vertex, but on the picture on the right, there is no vertex.
Yeah, so that's correct. So this is I suppose I'm sort of extrapolating the meaning of the graphics here. This is a kind of you know, visual aid. This is you could equally well state this thing without ever drawing this picture. I'm just doing this because later on, for what I want to talk about, it's useful to be able to perform this move. But you could basically define these two lines as precisely being equal to this productive indicator function. So if I have a line like this, where I have I at the bottom and j at the top, I had better have that I is equal to j, otherwise conservation will be violated. Okay, so you can extend the notation to include such a definition.
Thanks.
All right. All right, so now proposition number 3. I think it was 3 we're up to, yes. And so this is really the property that endows the model with all of its magic. And that's the famous Yang-Baxter equation. In particular, this is the property that leads to the model being referred to as an integrable or exactly solvable model. Okay, so the statement of this one will follow along similar lines to the unitarity. So we're going to fix a vector. So it's going to be I1, I2, I3, and then J1, J2, J3 that live in 0n to the 6. We have 6 indices. And then we're going to define 2 pictures, and then we're going to claim that they're equal. So here's the first one. I'll write it as L for, let's say, left-hand side. I1, I2, I3, J1, J2, J3. And that's going to be the following. So I'll have, again, one line that just goes straight. I'll have one line that migrates like this, and then the other line will migrate like that. And so this index is going to be I1, I2, I3, and I'll do it in such a way that the indices of a line are always going to have the same subscript. Okay, so this is line number 1. There will always be subscript 1 for this, and similarly for the others. So this is J2 then, and this is J3. And it's the same conventions as for unitarity. All of the internal edges, and there are 3 of them now. So let's just draw them. So this is an internal edge, this is an internal edge, and this is an internal edge. So all of those you have to sum over the possible states that live there and compute the quantity. Okay, so this is L. And then R is going to be the following. So I'll do the same thing. I'll fix the middle line. But now, maybe I'll make this line go like this, and this line go like this. Apologies for the shakiness of the picture. That's what we have. And once again, you have to sum over the states on the internal edges, which are these 3. Okay, so these are left and right-hand sides, and then the statement of Yang-Baxter equation is that L with all of its arguments is equal to R with all of its arguments, and this holds for all possible values of the 6 indices. I1 up to J3. Okay, so it's a lot of equations that hold with respect to these rational weights that we have defined. Okay, so yeah, I should say, so this holds as an identity.
Sorry, can I? Oh.
Yes.
So this was about so you said the weights should be between 0 and 1 in the beginning. So now you're forgetting this a bit, or so that this parameter and the Q parameter you should fix. And is it obvious that the Young-Baxter holds on on this where the weights take value 0 to 1 or not?
Let me finish what I was about to.
Sorry.
So I was a bit quick. So you still have these three parameters, x, y, and z, associated to the lines. All right, and again, the weight of each one of these will depend on the ratio of the two things, the two parameters that go through the vertex. And yeah, what I'm writing here is it holds as an identity of rational functions. In the four parameters x, y, z, and q. All right. So really, you can think of it as a kind of formal identity, where I don't actually say anything about the precise values of whether the weights are real or complex or anything like that. It's really some identity of indeterminates. But of course, for probabilistic applications, one can actually find values of all of these parameters, so x, y, z, and q, such that all of the weights are going to be positive. And if all of the weights are positive, because of the fact that the weights actually sum up to 1, clearly you're going to have some well-defined probabilistic models. So yeah, I perhaps should have said before, like really, all of these properties, unitarity and the Yang-Baxter equation, they have nothing to do with probability a priori. So these are just some algebraic equations that you can write solutions of. But there's an extra thing that you can add on top of this, which is the stochasticity. Okay? So it's like an extra thing that we add after we have both of these properties. Okay, so that's good. So now this is the third problem, which is to check the Yang-Baxter and check the Yang-Baxter equation in the special case I1, I2, I3, J1, J2, J3 being equal to 1, 1, 0, and then 1, 0, 1. Okay, so yeah, as I said, there are many equations here. Some of them are kind of trivially satisfied when you actually go through the check. But there are some that are really non-trivial identities of the underlying rational functions. And if I've done it correctly, this should be one such non-trivial case. Okay, so I just want to make a remark here. I kind of hinted at it before. So propositions 2 and 3 play the role of the Reidemeister moves 2 and 3 in knot theory. And to make that more precise, so there's a kind of catchphrase you can remember. So we may move lines freely as long as endpoints remain fixed. Now this is a very powerful tool. So this allows you to really do honest calculations using these models and derive some remarkable identities. And we're going to see some of them in these lectures. All right, so you can see that this is clearly true for both of the examples I gave above. So in the first case, it's obvious. The endpoints of the lines on this side and also on this side have been fixed, and all we've done is basically move one of the strands. And likewise, in the case of Yang-Baxter equation, all of the three endpoints are remaining fixed, and all we're doing is essentially taking, let's say, this strand here and pulling it across this intersection between these two lines. Okay. So this is a very important remark. This is a very important property, and this kind of underpins everything that we will do. So with this kind of this property, this now allows us to define unambiguously partition functions. So it allows us to define partition functions. Okay, so that's what I'm going to do now, and I'm going to define them in a kind of general framework, which is perhaps much more general than what we will actually need. But nevertheless, I like this kind of way of thinking about these models. So this will be definition, I think 4 or 5, I can't remember. Let's just say 4. So for any integer, so I'll have another integer in the game, which would be capital N now, not to be confused with little n, it's totally unrelated. So capital N, which is greater than or equal to 2, we're going to fix a permutation. So sigma, which can be written in the one-line notation sigma 1 up to sigma n, that lives in the symmetric group Sn. Okay, so we'll have a permutation. And then we're also going to fix 2 vectors, I1 up to In. And so these will be vectors of colors. Okay, so basically living in the state space, Cartesian product n times. And likewise, I'll have J1 up to Jn living in the same set. Okay. Then we're going to define the key object. Called partition function. And that's going to be the following. So it's going to be Z sub sigma. So sigma is our permutation. And I'll put I1 up to In as the first set of indices, and then J1 up to Jn as the second set. And so these are, again, going to have the interpretation of, these are going to be incoming colors, and these are going to be outgoing. So this thing is going to be equal to the following. So I'm going to draw it in a slightly schematic form, which hopefully it should be clear with explanation what it means. So I'm going to have this kind of black box where the lines can get tangled up and do whatever they want. But what really matters, according to the previous 2 propositions, is the endpoints of the lines. So this is really the important information. So I'll have some endpoints here and some endpoints at the top. And this one will have the state I1, I2, all the way up to IN. And at the top, I'm going to have J's, but they're not going to be ordered. They're actually going to be permuted according to this permutation here. So at the top, I'm going to have J sigma 1, J sigma 2, all the way up to J sigma n. And this quantity depends on n spectral parameters, which I can call x1, x2, up to xn. And so the convention here, where line, let's say where the line that begins at position k at the base of the lattice connects to position sigma k. Oh, maybe I should write sigma sub k. That's how I did before. Connects to sigma sub k at the top. Okay, so basically, for line number 1, which is here, line number 1 is going to migrate through this box, and it will then terminate at the position which is given by sigma 1, the first element of the permutation. And I do the similar thing for all of the lines, and in that way, I will obtain some sort of tangle of vertices that live in here. And according to previous propositions, we don't really care anything about what the lines do inside of that box, provided that they're not allowed, obviously, to have 3 lines intersecting at the same point. But as long as they don't do anything illegal like that, I'm free to move them around and do whatever I want.
Sorry, can I ask a question?
Yes.
Doesn't this always also depend on the height? I mean, you cannot, you need to know how many rows there are in between the bottom and the top, right?
Well, actually, in this picture, there are really no rows to speak of. There's just there's n lines, and I know where they begin, I know where they end, and this is enough to determine the object completely.
Oh, I see. So is it that there will also be n rows in between? I mean, you need to have intersections, right? For example, you cannot have 0. There cannot be 0 rows in between them, because then sigma would be forced to be identity.
We'll see some examples sort of right now, which should make the answer to your question be clear.
Okay.
Yeah. So I agree. The way I'm drawing it here is perhaps unfamiliar to people who maybe usually work with the vertex models. But yeah, this is somehow the most general setup that you can work with. And so now let's talk about some special cases. Okay, so 2 examples that will be prevalent in the lectures. So the first one is where, hopefully this should answer the question, is where I have something like this. So I have this kind of 2 sets of lines that cross each other and form a big cross, and then go out to their respective endpoints. Now this is the setup that is very familiar. Usually when people talk about vertex models, this is what they mean. Okay, so this will be our sort of primary object of consideration. And in this situation, we refer to this as colored paths in a quadrant. Okay, so the kind of scenario that we're going to see, just to give you a little glimpse ahead, is where I have a collection of colors, maybe that enter along these edges here. Let's say 1, 2, all the way down to n. And they're going to migrate through this lattice. Let's suppose all of these are going to be equal to 0. And they're going to terminate somewhere along the top. And the sort of choice that usually interests us is to have them going out through here and to have all of these being equal to 0. So this is going to give rise to pictures that might look something like this. This kind of thing. Okay, I by no means trying to do an accurate picture here, but hopefully you get the idea. All right, so this will be the main focus, particularly of the next lecture. That's what we're going to deal with. But there'll be another one, which is also very powerful and actually much less studied. And that is the case where instead of having these kind of two sets of lines that intersect in this way, we actually have three sets of lines. And in that situation, you can get this kind of picture. I'll try to draw this. So it's a kind of like grown-up version of the Yang-Baxter equation. So there are many Yang-Baxter equations happening here. Okay, and maybe I should complete this, so make these lines go down eventually, and make these ones go up. Okay, so this will be another type of object that we consider. And because of the Yang-Baxter equation, there is a freedom to redraw this thing in the following way. So that's going to be like this now. Something like this. Okay, so if I fix the states that live along the bottom to be some fixed choice, and I fix the states that live along the top to be some fixed choice on both sides of this identity, then this is a true statement. All of these are supposed to be fixed, and then you're summing over, the very complicated stuff that's happening in between. And so this particular equality allows you to do some pretty amazing stuff, and we'll see a few examples in the coming lectures. So this one sometimes colloquially referred to as the cube, and because you can kind of think of this this thing as being like two visualizations of a cube. Okay. Yeah, so I think that's basically my 1 hour. I got through almost everything I wanted to say. There is still one little thing, but I think we can do it at the start of the next one. I'll stop there.
Thank you. We have time for questions.
Thanks. Thanks for the nice lecture. I'm a bit confused about the point. So I think I understand what you meant in the definition for the partition function, in the sense you're just taking the lines from the bottom I1 to IN, and you're just connecting them up to J1 to Jn without adding any other sort of. So what I imagined in your figure, could you scroll up, please?
Just here?
Yeah. So the box that you drew where I1 and IN start from the bottom and J sigma 1 through J sigma n reach out at the top, I sort of assumed that there are other lines, sort of internal auxiliary lines that you could add, but you're not doing that at this point, right? So you're just...
Yeah, I think if I understand your question, so you're basically saying, imagine I've got some lines like this, yeah? So what I'm saying is this also fits into the formalism. It's just that in order to do this, I make these lines go up ultimately, and I make these ones go down.
Okay.
So even the case that you're talking about fits into this framework as well. And indeed, that's kind of what happened here in order to draw this picture. Because you could think of I could draw this in a more traditional fashion, and in fact, I will do that in the coming lectures. So I can have 3 lines, or 4 lines, whatever it is, that go straight like that, and then I can have like this. Right. So what I'm saying is all that's happened here is I just completed these lines by connecting them to the top, and these ones connect to the bottom.
I see.
That's all that's happened.
Okay. So, and then you sum over the extra ones, right? The extra horizontal ones that you add, you sum over all possible incoming and outgoing states for those. Is that... Well, maybe you'll explain tomorrow. So maybe.
Yeah, I mean, there are different things that you can do. So in all practical applications, these incoming ones will be fixed. So you make some definite choice for what they are, and then go with that. But you can then, for the outgoing ones, you can fix them, or you can sum over them, or you can perform partial sums. So there are various things that you can do. So in particular, one thing that you can do, which is kind of going to be hopefully clear. So if I take Z sigma for any permutation with some fixed incoming states, I1 up to In, and I perform a sum over the outgoing edges, J1 up to Jn. So just a free sum. Now this is equal to 1 for all I1 up to In.
Yeah. Okay.
Okay. So this is just a consequence of the stochasticity of the model. So in particular, whenever you see these kind of pictures, whether it's this picture here or this one here, there is some underlying probabilistic interpretation. You can really think of these things as inducing a distribution on the states that would go out along the top here.
Right.
So for given incoming states, you get some distribution for the outgoing states.
Okay. Yeah. Thanks.
I'm a bit confused by sigma. So first, sigma sub k is the same as sigma of k, right? Or is different?
Yeah, so I should have been sigma sub k is sigma of k. So maybe I should have.
So on the picture, if I look on the left, I see J sigma 1 to the left.
Right.
But
sorry, that's just a typo. Yeah. So let me correct it. So it should be like this. Yeah.
So if I read what you wrote below the diagram, I should also find sigma of 1 at the end of the red line that starts at I1. So I'm not sure where is J of sigma 1.
So right. Yeah. So it's a little bit confusing. Maybe I mean the inverse of sigma inverse. I always get confused on this point, but basically, in words, I can explain what's happening. So you take line number 1, and line number 1 needs to terminate at position sigma 1. So it should then be that Yeah, I need to I need to check actually. Yeah.
On top, you should write J sigma inverse of 1 then with that convention.
Yeah. Yeah, I'll need to clear this up, but thank you for pointing that out. Yeah. I think it's sorry, just to sort of conclude that this particular definition is not going to be too important in the coming talks. I just wanted to set things up at a sort of a fairly general level, but in what follows, we'll almost always be dealing with these kind of pictures, and then there will be no confusion. So.
Okay, I have a more general question. You mentioned that these colored vertex models, the ones you're presenting, are related to the SLN plus 1 Lie algebra. Are there colored vertex models for other Lie algebras, in which case maybe the discrete indices have to do with representation?
Yeah, so that indeed. So there's a whole family of these things. So let me I can try to do a little impromptu table here. So indeed you have this general situation. You have a vertex, intersection of two lines, and you should think of the two lines as corresponding to some representation spaces for whatever quantizer finely algebra you're looking at. So I, in general, have V and W. And so, well, let's suppose we're looking at, in this case, SLN plus 1. So in the case where V is equal to fundamental representation and W is equal to the fundamental representation, you get the model that we're looking at here. So this is our model. But indeed, there are other more general representations you can take. So I can take V to be, again, single box. And I can take W then to be a symmetric tensor representation, say, of weight M. I have a row of boxes now of size M. And this is usually what's called the higher spin, higher spin, higher rank vertex model that we also considered in that paper with Alexei Borodin from 2018. And then there's even more general case where you can take these things to be symmetric tensor representations of different weights. So this one of weight L and the other one of weight M. And this leads to pretty complicated solution of the Yang-Baxter equation, which was only explicitly written down in the paper of Bosniak and Mangazeev. I want to say from around 2015, 2016, I can't remember precisely. But, yeah, the explicit expressions for these things is pretty recent. And then, indeed, you can play this game even for other Lie algebras. So you can also look at the super Lie algebras. So SLM bar N. So what you get here is a kind of, so I should say these models up here, this is usually what's referred to as bosonic vertex models. The reason why they're bosonic is when you actually look at the higher spin representations, where you have stuff like this or like this. The higher spin representations, they allow you to have arbitrarily many particles at an edge. But these models you have here, these are of mixed, say, bosonic and fermionic nature. So basically the first index here, that's telling you the number of bosons that you have, and this is telling you the number of fermions that you have. So we studied these models. So it's in a paper with Amol Agarwal and Alexei Borodin. And this is from, I think, 2021. So we looked at these and also wrote down solutions of Yang-Baxter equation. And in particular, the sort of the case that's quite nice is where you have SL1N. So this is the sort of purely fermionic model. And this model has a lot of very similar properties to the model that we're going to look at here. But one thing that it doesn't have in common is it's actually not a stochastic model. So the weights do not satisfy a sum to unity property. And as far as I know, there's actually no way to cure that problem outside of a stochasticization procedure, but then that would turn the model into a dynamical model. And yeah. So yes, so one can also look at these and consider higher spin representations. And this, you can go on and also look at other vertex models outside of type A, but this is relatively unexplored. Hopefully that answers the question.
We have one more question.
Yes. So could you show the condition to have the positive weight in stochastic case in terms of Q and spectral parameters?
I'll just go up. You can tell me where. So you want to see actually the weights, or?
I'd like to know the condition to have positive weight.
Oh, how to have positive weights? Yeah, I didn't actually state it. So maybe we can just do it on this particular example here. So this is the 6 vertex model, but this case reproduces all types of weights. So yeah, it would work in general if we do it here. So you can take y to be less than x less than 1, and also take q less than 1. So if you take such a choice, with everything obviously being real, that should give positive weights.
I see. So is it okay to consider Yang-Baxter equation too with this condition? I mean, why?
Yeah, as I was sort of saying, it's kind of not really natural to, when you think about Yang-Baxter equation or the unitarity equation, you should think of this as an equation of rational functions or indeterminates that really has nothing to do with precise values of the parameters. So the kind of positivity or stochasticity, this is a property that you put on afterwards, but it shouldn't damage any of the properties of the model.
I see. Thank you.
Okay, so we have to stop here. So let's thank Michael again. And we have a break. We'll meet here at 11:30.
Thank you.
Thank you, Michael.